Look up at the night sky. What do you see? Is it just a canvas of twinkling lights, or is there more to the story? Countless stars, bright and faint, scattered across the vast expanse of space, each one a distant sun, a beacon of light in the darkness. These stars are gathered together in swirling galaxies, vast islands of light and matter, each galaxy a cosmic city bustling with stars. But what you see is only a small part of the story. The visible universe is just the tip of the cosmic iceberg. Hidden from our view, shrouded in mystery, lies a strange and invisible substance known as dark matter. It is a shadowy presence that we cannot see directly. It does not shine like stars or glow like nebulae. It is completely dark, eluding even the most powerful telescopes. It does not interact with light, making it invisible to our telescopes. We can only infer its presence through its gravitational effects. Yet, despite its elusive nature, dark matter plays a fundamental role in the universe. It is the glue that holds galaxies together, preventing them from flying apart. It is the unseen architect, shaping the cosmos with its gravitational influence. Without dark matter, the universe as we know it would not exist. Its existence is a profound mystery, one that has captivated astronomers and physicists for decades. They have dedicated their lives to uncovering its secrets. The story of dark matter is a tale of cosmic detective work, of piecing together clues from the faint whispers of the universe. It is a puzzle that challenges our understanding of the cosmos. It is a journey into the unknown, a quest to understand the fundamental building blocks of our cosmos. As we delve deeper, we uncover more questions than answers, but each discovery brings us closer to the truth. So, what is dark matter? Simply put, it is a form of matter that does not interact with light. We know it exists because of its gravitational effects on visible matter. Like a phantom puppeteer, it pulls the strings of the cosmos, dictating the motions of stars and galaxies. Imagine a spinning galaxy, a vast collection of stars, gas, and dust. If we could only see the visible matter, we would expect the stars farther from the center to move slower, just like planets in our solar system. But that's not what we observe. Instead, we find that stars in the outer regions of galaxies are moving much faster than expected. This unexpected behavior suggests that there must be some invisible mass, some hidden gravitational glue, holding these galaxies together. This invisible mass is what we call dark matter. The concept of dark matter might seem strange, but its existence is supported by a wealth of evidence from a variety of sources. These include the rotation of galaxies, the movement of galaxies within clusters, and the bending of light around massive objects. One of the most compelling pieces of evidence comes from the study of galaxy clusters. These are colossal collections of hundreds or even thousands of galaxies, bound together by gravity. By observing the motions of galaxies within these clusters, astronomers can estimate the total mass of the cluster. What they find is astonishing. The mass of the visible matter, such as stars and gas, is far too low to account for the observed gravitational effects. In fact, there seems to be about 5 times more invisible matter than visible matter in these clusters. If dark matter is invisible, how do we even know it's there? Astronomers have devised ingenious methods to study dark matter indirectly, by observing its effects on visible matter and light. One such method is called gravitational lensing. According to Einstein's theory of general relativity, massive objects can bend the path of light passing by them. This bending of light can act like a cosmic magnifying glass, distorting and amplifying the light from distant objects. By studying the distorted images of background galaxies, astronomers can map the distribution of dark matter in the foreground. These gravitational lensing observations provide further evidence for the existence of dark matter and its role in shaping the large-scale structure of the universe. Section 5. The Cosmic Web and the Sculpting of Galaxies. Dark matter is not just scattered randomly throughout the universe. Instead, it forms intricate patterns and structures that are fundamental to the cosmos. It forms a vast, interconnected web-like structure often referred to as the cosmic web. This web is a complex network of filaments, nodes, and voids. This web is made up of long, filamentary structures interspersed with vast cosmic voids. These voids are enormous, empty regions that contrast sharply with the dense filaments. The cosmic web acts as a scaffolding for the formation of galaxies. It provides the framework within which galaxies can form and evolve. As the universe expanded and cooled after the Big Bang, dark matter began to clump together under its own gravity. These clumps became the seeds for future structures. These clumps of dark matter created regions of higher density, pulling in ordinary matter like gas and dust. This process initiated the formation of stars and galaxies. Over billions of years, these regions of collapsing gas and dust gave birth to the stars and galaxies we see today. The cosmic web's influence is evident in the large-scale structure of the universe. The distribution of galaxies in the universe is not random. It follows the underlying structure of the cosmic web, a testament to the invisible hand of dark matter. This alignment reveals the profound impact of dark matter on the universe's architecture. Section 6. Dark Matter versus Dark Energy, Untangling the Cosmic Enigma. Dark matter is not the only mysterious entity lurking in the cosmos. Another enigmatic component known as dark energy is believed to be responsible for the accelerating expansion of the universe. While dark matter pulls things together with its gravity, dark energy pushes things apart. Together, dark matter and dark energy make up the vast majority of the universe's energy budget, leaving ordinary matter a mere cosmic afterthought. Understanding the nature of both dark matter and dark energy is one of the most pressing challenges in modern cosmology. Unraveling their secrets could revolutionize our understanding of the universe's origins, evolution, and ultimate fate. Section 7. The Search for WIMPs and Other Exotic Particles. What could dark matter be made of? Scientists have proposed a number of candidates ranging from hypothetical particles to primordial black holes. One of the leading candidates is a class of particles known as weakly interacting massive particles, or WIMPs. WIMPs are thought to be heavy, slow-moving particles that interact very weakly with ordinary matter. They are predicted by some extensions of the standard model of particle physics, which describes the fundamental forces and particles in the universe. Scientists are searching for WIMPs using a variety of techniques, including underground detectors, particle accelerators, and indirect searches for their annihilation products in space. The search for WIMPs is a challenging endeavor, but the discovery of these elusive particles would be a major breakthrough in our understanding of dark matter. Section 8. Unraveling the Mysteries of Dark Matter, a New Era of Discovery. The study of dark matter is entering a new era of discovery. Advanced telescopes, sophisticated computer simulations, and innovative experimental techniques are providing unprecedented insights into this enigmatic component of the universe. The Large Synoptic Survey Telescope, currently under construction in Chile, will map the distribution of dark matter in unprecedented detail using gravitational lensing. The Lux-Zeppelin experiment, located deep underground in South Dakota, is searching for WIMP interactions with unprecedented sensitivity. These and other cutting-edge experiments hold the promise of unlocking the secrets of dark matter, shedding light on one of the most profound mysteries in modern science. The quest to understand dark matter is a journey into the unknown, a testament to the boundless curiosity and ingenuity of the human spirit. Section 9. Dark Matter and the Ultimate Fate of the Universe. The study of dark matter has profound implications for our understanding of the universe's past, present, and future. This mysterious substance, which does not emit, absorb, or reflect light, makes up about 27% of the universe. Despite its elusive nature, dark matter exerts a gravitational pull that affects the motion of galaxies and the structure of the cosmos. The amount of dark matter in the universe will determine whether the universe continues to expand forever, or eventually collapses in a big crunch. This cosmic tug-of-war between dark matter and dark energy shapes the ultimate fate of everything we know. If the universe contains enough dark matter, its gravity could eventually halt the expansion and cause the universe to contract. This scenario, known as the Big Crunch, would see galaxies drawing closer together, stars colliding, and the universe shrinking back to a hot, dense state. However, if the amount of dark matter is below a certain threshold, the universe will continue to expand indefinitely, becoming increasingly cold and dark. This endless expansion could lead to a state known as the heat death, where stars burn out, galaxies drift apart, and the universe becomes a vast frozen expanse. The fate of the universe hangs in the balance, and dark matter holds the key to unlocking this cosmic mystery. Scientists around the world are conducting experiments to detect dark matter particles and understand their properties, hoping to shed light on this invisible force. As we delve deeper into the enigmatic realm of dark matter, we embark on a journey of discovery that could illuminate not only the distant corners of the universe, but also the fundamental nature of reality itself. Each new finding brings us closer to understanding the grand tapestry of the cosmos and our place within it.